All right, here we go, folks. We are in the home stretch. Let's see what we can do with this. Number 12. Number 12. They tell you right away it is a standing wave. They give you the length of the string, and they say it vibrates in 4 segments when driven at this. So they give you the length of the string, and then they tell you 4 segments. What does that look like? What they mean is this. That's an ugly representation, but stay with me. 4 segments means 4 bumps, but each bump is a half wavelength. And remember, our equation was L is N half wavelengths. So whether you call them segments or bumps or half wavelengths, that is N. N equals 4. So when they say 4 segments, they're telling you N equals 4. And then they give you the frequency. What do they want? Find the wavelength, and then find the fundamental frequency. So there's a couple things that we can do with this. How do you find the wavelength? This is the simple fundamental idea. Let's not use that word. This is the basic idea behind standing waves. The length of the string has to be some number of half wavelengths in order to form a standing wave. But look what they've given you. They've given you L, they've given you N, and they've said, what's the wavelength? You should be able to see visually the wavelength is just half of the length of the string. Now they want, what is the fundamental frequency of the string? What did we just say in the previous problem? We said that F1 is V over 2L, but F4 is 4 times V over 2L, because any frequency is going to be N times V over 2L. But what that means is F4 is 4 times F1. They are giving you F4. Get F1. That was number 12. All right, number 13. A string with a mass of 6 grams A string with a mass of 6 grams and a length of 5 meters has one end attached to a wall. The other end is draped over a pulley. This is starting to sound familiar. And it has a hanging mass on it of 3 kilograms. Wait a second. It's almost like they were spying on us doing Lab 12. If the string is plucked, what is the fundamental frequency of vibration? Fundamental frequency means standing wave. You're dealing with standing wave. Fundamental frequency means you are dealing with a standing wave, and fundamental means n equals 1. Right? So what do we know about that? We know that the fundamental frequency is NV over 2L. That comes from that expression combined with V over lambda F. We've already talked about that several times. If you combine these, you get this. It's what we just used for lab. There's not a whole lot more to it. But what do they give you? They're giving you this. Let's see, let me draw a quick picture. We're going to connect it to the wall. And this picture should look familiar because it is what we did in lab. So this is big M. They're giving you the hanging mass, and they're giving you the mass of the string. So I'm going to call this the mass of the string, and they're giving you the length of the string. Now this is a little bit cheesy, and we addressed this in lab. When we got mu, mu was the mass of the string divided by the length of the string. When we got mu for lab 12, I had to untie the string, and we got the mass of the entire string. And then we measured the length of the entire string. That's how you have to do it. But look what they're doing in this problem. They're getting really lazy. They can do that in homework problems because you can make stuff up. But in lab, you can't. Lab, we had to do it properly. We got the full length of the string. But then when we did our standing waves, the standing waves only traveled here. The standing waves did not travel the full length. So the full length of the string was different from the length that we used in part B for the standing waves. In this problem, they're just ignoring that and they're just using the length for both. So improper of them, however, you just got to go with it. And so this is going to be the given length L. I just want to bring that up because in lab we had to do it properly, and I want you paying careful attention to the different lengths that we had to deal with in lab 12 to do it properly. Right? There's a difference between the full length of the string and the length that the standing waves can travel on. In this case, though, they're trying to describe mu. And what can you do with mu? You can get v, where v squared rather, is the tension over mu. So notice, they're giving you the information you need for mu. What is the tension? The tension is equal to, just like we did in lab, the tension is the weight of this guy hanging on the end. Exactly what we did in lab. Notice I've used big M for the weight hanging on the end, and I've used little m for the mass of the string. It's important to distinguish those. So what can you do with this? I would recommend, they want the frequency. They're giving you n equals 1. They're giving you L. V is the square root of tension over mu. That can go here. Mu is mass over length. That can go in here. You could calculate all these things, but I will implore you, give your brain a chance to do some work, right? Instead of punching a bunch of buttons, my goodness, nobody wants that. Give your brain a chance to do some work. Put these together algebraically. I would do this. I would square both sides of this equation. If you square both sides of this, you get f squared, n squared, 4, l squared, v squared. That avoids a square root, because once you have a v squared here, you can put tension and mu in there. And then you can replace mu with mass and length, and you'll see some stuff cancel out. After you have it all canceled out, calculate f squared, and then simply take the square root. That gives your brain a chance to do a little bit of exercising, which is going to be good because you got an exam 4 and the final coming up. But it also minimizes your button pushing and minimizes your chance of making a mistake when you go to calculate the frequency. Anyways, put it together, knock it out. Let me check my time. We're at 8 minutes. Okay. All right, folks, this is our last one. Number 14. Let me get rid of all this, and we'll prepare ourselves for number 14. Man, I'm almost inclined to skip 14 because I did a really good write-up of this one. But let's see. The top string of a guitar, guitar strings. Fundamental frequency, there we go. Fundamental frequency of 300 hertz when it is allowed to vibrate as a whole along its 65 centimeter length from the neck to the bridge. A fret is provided for limiting vibration to just the lower 2/3 of the string. So this is how guitars work. If you don't touch the string and just strum it, it will vibrate in the fundamental frequency for the full length. But if you use the fretboard where you are then putting your finger on the string, in essence the finger acts the same way as the pulley did in our lab 12. The standing waves on that string will reflect back and forth at your finger instead of the full length. So using the fretboard effectively changes the length of the string that the standing waves are allowed to travel on. What you should see, if you play guitar, is, and you know this, is as you move your finger down the fretboard, the frequency that that string plays increases. Why? Because as the length gets shorter, the wavelengths get shorter, so the frequencies increase. In essence, it's like turning your guitar into a ukulele. When you put your finger further down the fretboard, shorter strings, it's effectively making them shorter. Now what's my time looking like? All right, now we're at 9 minutes. So here we go. Guitar string. I'm going to do this. I'm going to go ahead and make this number 14, and we are going to talk about a guitar string that has this length, and they give you the full length of the string. They also tell you that F1 is 300 hertz for, I'm going to go ahead and call that L1 for the full length. Then they say we're going to provide a fret, right? So this is the bridge at the lower end, right, where the guitar is, right? And this is the neck up here, right, where you've got the little tuner guys up here, like so. But we are going to provide a fret to the lower 2/3 of the string. So here we go. We're going to put the fret here. I'm going to call this now, I'm going to call this L2, okay? And what do we know? L2 is 2/3 of L1. And they say if the string is pressed down at this fret, what is the new fundamental frequency? Well, what do we know about frequencies? Frequencies are NV over 2L. In both cases, we're talking about the fundamental. They've given you two cases to compare. All right? So I am going to call this, the new fundamental, I'm going to call this F2. And what we can write is F1 is going to be V over 2L1, and F2 is going to be V over 2L2. So they're giving you two situations to compare for part A. And notice, V is the same in both, because that string, whether you are putting your finger here or not, that string has the same density, and it has the same tension. You don't change the tension in the string by putting your finger on it. The tension is changed up here, right? With the little. So, what can you do with these? Notice F1, F2, they want you to find F2, they give you F1, they give you L1. In essence, they give you L1, right? But they don't even need to, because L2 is 2/3 of L1. You could write both of these as V equals stuff and V equals stuff, and then set them equal. Alternatively, you could just divide the equations. However you want to handle it, put these equations together, pop it out, although I'll give you a little hint. The frequency is inversely proportional to L. So if you multiply L by 2/3, that's like multiplying the frequency by 3/2. And you know the frequency is going to come out higher, because if we make L shorter, just what I was just talking about, if we make L shorter, the corresponding frequency should be higher. Then they say, let me check my time, the guitarist can play a natural harmonic by gently touching the string at this fret and plucking the string about 1/6 of its length from the bridge. What frequency will be heard then? That's a sneaky question, but here's what they are describing. For part B, they're saying we're not going to hold it down here. We are just going to keep the string from vibrating there. If you hold it down, you get the same situation that we had for our string in Lab 12, where the pulley, it was pinched against the pulley. And if you hold it down, then we get just this string is where the wave can travel. But let me move this. This is like a third. Our 2/3 should actually be like this. So this is 2/3 of L, and this distance is 1/3 of L. So now they say, what if you just put your finger here without holding it down? The consequence of that is it keeps this point from moving, but it still allows the wave to travel through. The restriction is this now has to be a node. And so what frequency will this wave oscillate at? They're giving you some clues here. The clue is you have to have a node 1/3 of the way, but you have to have an integer number of half wavelengths along the way, which means the wave that it will oscillate at will look like this. The longest wavelength you can get will be n equals 3. And so for part B, we use, what they are describing is we use the full length of the string, but now n equals 3. And so they want you to find F for n equals 3. But what do you know? You know the fundamental when n equals 1 was 300 hertz. And what do we know about the harmonics? They are integer multiples of the fundamental. So the clues they're giving you are basically come down to saying, well, find n equals 3. What do you know about the frequency for n equals 3? It is 3 times the frequency for n equals 1. And that is the end of chapter 13. I hope what you've seen here is that everything we've done here, the Doppler problems actually required pictures and a process, but even those were about as simple as they can get. The rest of this was just like chapter 12. A lot of little definitions, throwing information at you and asking you questions that you put together and you pop out answers. Folks, that is it. I'm going to go ahead and shut down this video before it gets to the 15-minute mark. And that's the last problem that we're doing for this semester. So if you got to this point, congratulations. You made it. All we got to do is wrap up our last exam, wrap up the final, take a break, and reflect on what we've accomplished.